Hey folks, Quill18 here, and welcome to a video where we discuss ECS, the Entity Component System that is coming for Unity. Now, at the time that I'm recording this, Unity 2018.1 is out, and the ECS system is still being developed. It is available in the preview build. It may, in theory, make it to the 2018.2 release build, but it's still a little bit in flux. But it's gotten a lot of attention, and a lot of people have asked me questions about it. So we're going to do some videos, plural, to address this. In today's video, we're not actually going to be running actual ECS code. In fact, I am not on the beta build. I want to talk about the theory behind ECS and also what you can do today that is very ECS-like, that gets you almost all the performance gains of ECS, and will also prepare you for ECS in the future. So what the heck? First of all, slideshow. Yes, it's slideshow time. What's the big deal with the Entity Component System? What's the idea? Maybe you haven't heard of it before, or you have heard of it and you don't quite get it. The goal of the Entity Component System is to let you process a lot of data very quickly. That's the point. The examples that Unity has been putting out to sort of highlight ECS are things like sort of Total War style battles where you've got 10,000 soldiers on both sides and they're all moving at the same time, and there's explosions and particles and they're all going crazy, and it's all operating at a relatively quick rate. So in a way that you might not think would be possible to do in Unity itself. And that's sort of true in that if you're just using a bunch of game objects with regular mono behavior components on those game objects, you wouldn't be able to run that many things simultaneously, and it comes down to a few different things. Now, ECS is not actually just one thing. The Entity Component System really encompasses data reorganization, a different way to store your game data that means that you have dramatic performance improvements simply by not breaking the CPU's cache all the time. And we're going to talk about that. That's actually going to be one of the main topics in this particular video. This by itself is where almost all the performance gains from ECS is probably going to come from. Simply organizing your data in a better way that lets your CPU burn through the data so much faster. It's also, as a side effect, going to lead to data that's a lot more thread safe. A lot of people criticize Unity. Oh, it's not thread safe, it's not multi-threaded. Well, first of all, Unity does use multi-threading out of the box. It uses some of that already for some of the physics systems and sound systems and graphic systems and different things like that. The thing that is not thread safe in Unity is interacting with things like the game object class, right? Objects of the game object class, because they contain a lot of data, and they didn't go and put a bunch of like locks around each field in there to make it thread safe, because that would slow down the entire engine to an apocalyptic level. Just making things generically thread safe by putting locks around things is not really viable. However, you can make individual things very easily thread safe by segregating out your data and reorganizing your data in smarter ways. And it's a two-step thing. It's a two-reward thing. You improve this cache performance, and you get thread safety. Another part of ECS is the new Unity job system, which is really just a wrapper class around threads, which is in the current version of Unity if you're using it today. I mean, it doesn't do anything special. It's just a handy class to work with for using threading and things like that. One of the big things with multi-threaded code is that really there's sort of three, I'm going to make the case that there's three sort of general use cases for multi-threading. The one people think about all the time is a secondary or multiple different threads that run constantly next to the main thread at the same time. And really, the examples for stuff like that are always things like, oh, your sound engine, right? So that the sound keeps playing even if the main game thread starts to lag out, or the UI thread so that it responds to that. Well, I mean, unless you're writing your own game engine, that really doesn't come up as a use case that you're going to see. That use case is inherently desynchronized from your game logic. And so your actual game logic isn't really going to run in this concurrent nonstop thread like that all the time. It doesn't really make sense. Instead, you've got two other use cases for threads that you're going to see much more often in game development, and they're both sort of synchronized to your game. One example is, hey, I've got I've got this kind of long job, like maybe a pathfinding thing, right? I've got these units, they want to do some pathfinding. The problem is, for me to pathfind throughout my map, because it's a huge map with lots of complicated bits and bobs over here, it actually takes me multiple frames worth of time. Like, if my frame rate is supposed to be X milliseconds, then this pathfinding takes longer than that to work out. And I really don't want the program to stall while a car in City Skyline tries to figure out how to get from point A to point B. So that's a great example of spinning something off to a separate thread, because it's sort of an isolated one-shot job. It just needs access to basically a copy of the map data, and that's it. And you just tell it, listen, find how to get point A to point B, and then let me know when you're done. And then you just forget about it. And then, 3 or 4 frames later, something like that, the thread finishes, and it sends a signal back to your main thread and says, I figured out how to get from point A to point B. It is this route here. And then your main thread takes that information and goes to town with it. The third use case is more something like, listen, every frame I've got to do, say, these 4 different things. And they're all pretty, work-intensive things. And if I try to do them back to back to back to back, it takes too long for my frame to operate, and my frame rate starts to suffer. But these 4 jobs are really separate and distinct. They don't interact with each other in any way. So at the start of each frame, I'm going to start 4 threads to do those 4 jobs simultaneously. My main thread will probably then wait for those 4 to finish, because they're happening simultaneously on different cores. When all 4 are finished, then I can go and move on with dealing with the rest of the frame logic. And so now something that used to take, 4 units of time now takes 1 unit of time, but it's still super synchronized. And that's really that final case, that one there. That's exactly what the entity component system is built around. It's about running multiple segregated tasks simultaneously once each frame. These are not permanent threads that are running all the time in the background. These are threads that get spawned at the start of a frame, run, stop, and then you finish doing your update. Basically, yeah, every update, you're going to start a bunch of threads to do some jobs at the same time. They're going to finish, and then you're going to continue on with your update, dealing with stuff that maybe can't be separated and does interact with each other. So yeah, that's the job system. And then there's some glue in between to link your data and your job system, and that's what ECS is. And in fact, in my opinion, I'm going to make the case that ECS itself, right, ignoring the data reorganization and ignoring the job system, it's not very important, right? The data gain, the whole reason you're doing this is to get performance gains, and that comes from the data layouts, but probably 90% of it will come from the data layouts, and then the rest of it will come from the threading. ECS itself is still in development and changing. If you try to find documentation for it online, some of it's already a little obsolete and refers to different ways of writing code that don't apply anymore, and there's not a full suite of documentation yet either, because at the time that I'm making this video, it's not actually released. So it's a little tricky to jump right into ECS, but again, we can do, like, 99% of what ECS does, we can do ourselves right now. Because mostly it's just a series of wrappers and a little bit of compiler magic that saves some typing for you. I will say this, the dependency system is really cool, and we'll talk about that in the future video. But yeah, so let's move on. So actual ECS video will come a little bit later, probably until the code's a little bit more stable and final, maybe when it's actually released as a release version, or maybe still in one of the betas. But we're going to get to it soon. But again, we can implement all the good bits of ECS today. Well, some, and then some in the next video, because we've already taken up 8 minutes and we haven't started any of that. Let's talk about data layout. So the core idea here is your CPU, right? Your processor, which is going to do the work, can only work on data that's in its cache. That's memory that's basically on the CPU itself. Most of your data is sitting in RAM. Now, pulling info from RAM into cache is slow. It's extraordinarily slow. You can do 100 things on your CPU in the amount of time that you're waiting for a little bit of data to be pulled from the RAM into the cache. And so if you can somehow write code that is better about using the cache and doesn't force as many fetches into RAM, you get code that is much, much faster. So instantiating objects, whenever you create a new object in C#, it allocates memory in a completely random place in RAM for that object, right? You can't predict it, and it can be scattered in a variety of different ways. This is even true if you're instantiating an array. So let's say you want an array of 100 game objects or units or whatever, right? So this is a class. You have some sort of class, and you're creating an array with 100 instances of that class. Each instance of that class, each object, is still going to be scattered randomly throughout memory. For different levels of accuracy of that, but it can be scattered completely randomly through memory, especially as you get more and more memory fragmentation. Now, the array itself is going to be a continuous blocks. In RAM, your array is going to be 100 things back to 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 back. But those 100 things will simply be pointers to the actual objects that are going to be scattered all over the place. So this means that iterating through an array of objects means that you have to constantly load random parts of RAM that the CPU cannot predict, and it's very slow. So item one, so you've got, the CPU can load the whole array into its cache just fine. But again, this is an array of pointers. And so it looks at the first item and it's like, oh, I have to grab the object from this place in RAM. And then it looks at the second item and it says, oh, I have to grab this from this place in RAM, and so on and so forth. So what can we do? Well, before we get into the what can we do, I want a quick refresher on the difference between a reference type and a value type, just in case someone is not completely up to date on that kind of thing. And so we'll try to go through this really quickly for the people who have been around for it. So if we bring up some code over here, we're going to do a quick little example of some code. So first of all, I have a little dummy class here called myClass, and it just has a single field in it called myInt. That's all it's got there. And then we've got some piece of code. It doesn't matter, what this is contained in. We've got some piece of code. So we instantiate a new variable. We create a new variable called A, and we stuff the value of 1 into it. And technically A, and this number 1, exists on the start function stack. So each function sort of has its own stack, its own personal memory space. It's always contiguous. Stack manipulation versus heap manipulation is not actually the important part of this example. It's the sort of random allocation versus not. But for the sake of completeness, there it is. Now, with this value, we can call a function. So we call this function called passByValue, and we feed it A. So in this function here, this is a simple function that just takes a single integer. Now, this is the value of 1. So A has the value of 1, and it is this value of 1 that gets passed to this function here. So on passByValue in its stack, it has a completely separate copy of the number 1 on its stack, and I, our variable I here, is just linked to that value 1 on its stack. If we set I to be equal to 100, we just change on passByValue stack, we change the 1 to 100. This has no impact whatsoever on the 1 that is in start stack, aka this A over here. A is still worth 1, so if we do a debug over here, it would still put out the number 1. That's because we just passed the value of 1. Now, when we're passing by reference, things are a little different. So we're going to create an instance of our class here. We're going to set it into B. So we've got a new instance of my class, and in this my class is B. It's got a property or field, myInt, over here that we're setting to a value of 2. We're then going to call passByReference. So passByReference accepts a class, a myClass instance over here, which we're calling C. So we have B in start and C over here. Now B and C are completely different variables. They're in completely different stacks. They occupy completely different areas of memory. B and C are two totally separate things. However, the value of B and C is exactly the same thing. B and C both contain, they're both pointers. They both contain a memory object, okay? An area in RAM. So we instantiated this myClass. It got created somewhere in RAM, and what this returns is it returns the address of this object. So we have the address of this object stored in B. So the value of B is the address of this object. And we actually pass the value of B, which is an address, to this function. So C contains the same address. Now, if we then go c.myInt, and then we set the value of myInt to 200, this is affecting the same object in memory. B and C both point to the same object, so we're changing the value over there to 200, which means when we come back over here and we output b.myInt, B is unchanged, but myInt is now 200 instead of 2. In this function, if we decide to set C to a new instance of class, so this is going to create a new object of my class somewhere in memory, and C will now point to that. B is still pointing to the old object. C is pointing to the new one. So there's really no difference between passing by value and passing by reference. Either way, you're always passing by a value. It's just that sometimes your value is a pointer to some piece of memory. So this matters because when we're talking about data layout, and we're talking about how to speed up processing, say, a large array of data, we want to mess with the difference between references and values to optimize things. So when a CPU fetches data from RAM, it actually doesn't just load one thing at a time. It actually loads a whole chunk of RAM into its cache at one point. Just because of the way the pipeline bandwidth works and whatever like that, you don't just load one byte, you load a chunk of bytes, which the amount of bytes you load depends on things. We don't care about the numbers here, whether it's 32 bits or 64 bits or something else. Or, sorry, not bits, but bytes in this case. We don't care about the specific numbers. The important thing is that it grabs a chunk of data at once, not just the one thing you're looking at. And if we only use one part of that chunk, one part of that memory block, and then we have to go and fetch an entirely new memory block for the next operation, that's slow, because each one of these fetches is apocalyptically slow in CPU times. However, if we can do a bunch of work on the same block at once, that's very fast. If we can minimize how many fetches we do, that's incredibly speedy. So what's bad would be iterating over an array of references, such as an array full of game objects. Because if we go, we start at, array 0, that's one fetch. Array 1 will be a completely different fetch because it's from a completely different random location in memory. And it's even worse if we have to do a lookup, if we have to look up a reference to reference to reference. So we first have to do a lookup for the game object, and then we have to find a lookup to the reference of the transform, and then we have to do a lookup for the reference of the position, although position's value property, so maybe it doesn't matter as much. But anyway, many fetches to random memory, it's bad. So what would be good? What would be good would be iterating over arrays where the array itself has the value that we want in the first place, as opposed to a reference to the value. CPU optimization will then lead to insane speed. So let's do an example. So first, the bad iteration example. So here we have some sort of array of game objects. We don't know how it got populated. We have some array of like 10,000 game objects that are in here. And this is an array of references, of course, right? So the array itself is just an array of pointers to 10,000 different random locations in memory. So we're going to do some sort of loop over here where we're going to loop through every item in the array, and then every other item in the array, slightly optimized with this I+1 stuff. But basically, what we're trying to do is we're trying to compare every item in an array to every other item in an array, and we're just checking to see which one's higher up, okay? Which one has the higher Y value than the other. So sort of stupid busy work. But the point is that it's gonna try, the CPU is gonna have to read the chunk of memory where array of references I is, and then it's gonna have to read a completely different chunk of memory to find where array of references J is. So, okay, sorry, it can keep this whole array of references in memory. But again, array of references I is a pointer to a completely random chunk of memory, and array of references J is a pointer to another completely different part of memory. So it keeps having to fetch it. Worst case scenario, depending, well, it'll probably keep I around because you can, the cache can keep multiple chunks in place. But worst case scenario, it's gonna have to do 1 or 2 memory fetches on every single loop of this. And again, if we have 10,000 items, that's insane. It's so slow, it's so bad, it's so terrible. However, if before we start this loop, we put all of our position values into an array of vectors, okay? Or something, this could be ints, this could be whatever. So vectors are they're values. They're structs, actually, but they're value. They're not a reference. They're not a pointer to something else, which is why you can't ever do vector 3a is equal to null. Vector, this is a value that is supposed to have an actual value. It's not a pointer to something, so it can't have a value of null, right? So if you have a game object, b, you can say null. This is a pointer to nothing, right? This is a pointer to nothing. But vector is not a pointer, it's not a reference, it's a value, and null's not a value, so that's not allowed over here. So here we have an array, and in memory, this is stored in memory as vector, 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 10,000 vectors in a row in memory. And that means when you loop through this here, and it grabs a chunk at a time, most likely we're going to be able to do multiple loops here, right? Again, it'll probably have the array of values I in one chunk, and then it'll pull a separate chunk for your first J. But that first chunk that it pulls in for J, it's going to pull in the first J and like the next 10 J's at the same time because it reads in a chunk of data at once, which means it's going to be able to process 10 J's in a row before it has to do another fetch. and that is so much faster. Not only that, modern CPUs are pretty damn smart. When you're iterating over stuff like this, they tend to do all kinds of automatic optimization where they start prefetching the next blocks because they think there's a good chance you're going to want to read more stuff in a row. So in a background, it's already loading the next block of memory so that by the time you need the next block, it's already there. This is so much faster than the previous version. It's maddening. You can make your own examples if you want and do some benchmarking, but it is ridiculous. Okay, so we've got the bad, we've got the good. So how do we work with that? Well, let's talk about the whole model view controller kind of architecture. This is something that as someone who worked as web developer for a very, very long time, that was something heavily ingrained in me there, but it's actually a type of organization of your code that actually works extremely well for games, in particular, complex enough games. If you're just doing something like a pure sort of, I don't know, very physical based first person, running around a physical world, then this sort of thing matters less because like the game logic is the physical simulation, is the view, right? But for a lot of other games, there is, in a sense, there can be a very strong distinction between your game data itself versus the visuals you show people. In particular, if you have a game where there's a lot of stuff happening off screen or something of that nature. We put this to really good use during Project Porcupine, for example, because we knew we wanted to have a world that could have really big maps with tons and tons and tons of tiles and lots of units moving around all the time. But having those sort of rendered and represented by game objects all the time could be very slow. In that example, in Project Porcupine, we didn't orientate things in a sort of entity component system, and we didn't take advantage of sort of cache manipulation, but we still had a very distinct split between the model, the view, and the controller. In this case, model is your data, the view is your interaction with the user, so it's your graphics, and your input controls and things like that, and the controller is what links the two. Generally speaking, your controller would be like the mono behavior attached to a game object or something of that nature. And that links the two. So the model looks after itself, the view looks after itself, and the controller sort of links the two there. The advantage of doing this, of segregating your data from your presentation layer, is it keeps all your data in one area. It actually leads to cleaner, less buggy code because you don't have a bunch of mono behaviors all trying to interact with your code in a variety of different ways. You have one place that takes care of your data and one entrance and exit from your sort of data storage area. It also simplifies saving and loading a lot because then you just have one area again of memory where your code is, and you don't have to worry about going through all these mono behaviors and weird stuff. It also makes it a lot easier to write certain types of unit tests, which is great. But most importantly, it makes it most importantly for this video, it makes it much easier for us to boost performance with data layout optimizations, and it makes multi-threading viable. So what we're going to do here is we're going to go old school for this. This is going to be really weird because everything that we've learned for like the last 20 years is like, oh, object-oriented design is the best, right? And for a long time, it was like, oh yeah, and complex inheritance and multiple inheritance. We've been moving away from this, right? We now know that like, okay, inheritance, yeah, we do a little bit of inheritance, but really not so much. We're instead using components already, right? Like mono behaviors and components that we slap onto game objects. Turns out that's pretty strong. So there's a little bit of movement from this like class hierarchy that's been developing for a while, especially for game development. We're finding out that the strict hierarchy doesn't really work so well. And this is actually going to go even further than that. It's sort of like back to the C days before there was classes, and your data for things would really be kept in simple arrays with common indexes. You would have one array for like your unit's position, and another array for the health of all your units, and another array for the names or the graphics of all your units, etc., etc. In fact, and we're not doing this today, but we're even going to take a step away from managed memory, right? C# is a managed memory environment where you never have to go and delete or free up an object. Eventually, it just gets garbage collected. But of course, we know garbage collection can lead to certain performance problems. Also, the managed memory system has certain implications about how data is stored in memory, and we might want to go and move away from that and go to a slightly more manual, somewhat more native memory architecture for some of our data, but that's going to be a future video thing. So this is the final slide of the video. Let's do an example of how we might do this. So we're going to have this unit manager class, and it's worth noting we could have called this class entity manager. Basically, what we're creating here is a very simple and incomplete, bare bones kind of version of what the ECS, the entity component manager in Unity, is going to do. This is effectively how it's going to work. So if you understand the simplified example, you will understand how to use ECS. Although, again, there's sort of there's you know, syntax and a little bit of what I call compiler magic with special tags, like I have like inject and different, anyway, there's other things we're going to do to like use all of the tools, but you'll understand how it's supposed to work. Let's ignore this struct over here for now. We'll come back to it. So we have the static class called Unit Manager, and it's going to have a bunch of arrays in it. So we're going to keep note of what the capacity of array here is and what the first empty index of the array is. Right now we've got 0. That's fine. So our first array, our first set of data to describe our entities is, hey, is this entity alive? Again, it's going to be an array. Is it alive? So at any point you can find out, so every entity in the game. So let's play, you're making a game about spaceships, right? Some sort of shmup. And you've got some unit out there. It's an enemy. It's an enemy. And enemy number 17 or entity number 17, we can find out, hey, is enemy 17, right? Is it alive? What is enemy 17's hit points? What of its armor? What is its position? So instead of having a single object, probably an instance of a class that encapsulates everything about the enemy, instead we're encapsulating, wow, that's hard to say, the details and having a single array for one piece of data indexed based on that. So all these arrays, is alive, hit points, armor, position data, will all have the same size, and the entity referred to by index 17 is going to have its data spread across all these different arrays over here. And it's like, man, it does feel like a little bit of a step backwards, and in a sense, it is a step backwards from object-oriented design. But we're actually, later on, we're going to be using a variety of things to make it feel not so backwards and not so cumbersome to manage. And in fact, that's, again, what the ECS is going to do for us. And what it does do, again, is make the performance of the program so much better. Cache optimization, multi-threaded options, and the greater ECS system. So we've got an array to track things if they're alive, and then some other stats about them spread out over here. I also want to keep track of what units have died, because let's say we create an array of, like, we've got room for 100 units, and this starts to get populated, right? And then at some point, unit 17 dies. Well, I'm not going to shrink the array, but at some point the array is going to fill up, right? At some point, we're going to want to spawn the 101st enemy of the game. And what we're going to do for that is we're actually going to grow the array. But we don't want to keep doing that and end up with a bunch of empty spots in an array that are for dead enemies, because then this keeps growing and growing and growing and growing, and eventually we won't be able to grow the array anymore. We'll have a bunch of wasted space, and maybe we'll run out of RAM. I mean, you know, maybe it could happen, sure. So when a unit dies, we're going to keep track of its position. This is just a queue of integers. We're going to keep track of its position in the array, and then we can go and stuff something back in there later on. So we've got this. We've got a bunch of notes in here that you can read, right? So we need to keep track of which entities are alive, fragmentation talk, so various bits of info that a unit might have. You could almost call these values components that belong to an entity. See what I'm doing there? For data that's almost always used together, it might be convenient to group them together into a single struct to organize our data. Again, putting in a little bit of maybe that object-oriented sort of idea here. So unit position data, which is a struct that I defined up here that we skipped. Structs and classes are almost entirely the same thing in C#. There's some slight differences when it comes to the default constructor, and a couple little things here and there, but really very little. The biggest difference for our particular purposes here today is that structs are value data. Again, a vector is actually a struct. Vector 3 is a struct. You can't make a vector that is null. You're not allowed to do that. There you go. Wow, there's lots of things going on here. But you're not allowed to do that. Yeah, it's because it's not static. Is the other complaint here. But you're not allowed to do this because this is not a reference type. It doesn't point to memory, so it also can't point to null memory. It has to have a true value. It's like you can't have integer static integer I equals null. You can't do that. The integer I has to have an integer, has to have a number in it, and that's the same situation. So this struct is a value. It doesn't point to random memory somewhere. It is its own data. It's never a pointer. It's always its own data, which means if you make an array of a struct like unit position data, it's all going to be contiguous and in one big chunk. Now, if you have a very large amount of data within a struct, after a certain point, it doesn't really help to have it be a struct. There's like a rule of rule of thumb that I think that Microsoft has said for C#, like if your struct is larger than 48 bytes, not bits, but bytes, I think it's 48, I might be misremembering, but it's something like that, then you may as well just use a class. Just because you stop to lose, you're no longer gaining the sort of cache optimization effects and different things like that. And you do have to, when you're calling a function and you're passing a struct, you're making a whole copy of the entire struct and passing it to the function instead of just passing it the copy of the pointer, right? So calling functions with structs, if the struct is quite big, becomes very slow because you have to do a lot of memory copying. There's also, you have to be really on guard with having reference data inside of a struct. Because if you do this sort of thing, you can be really surprised at some of the behavior that happens because of the way copying works and value things, and you stop. Anyway, probably a good idea. One of the rules of thumb is don't put reference type data inside of a struct, because you might screw yourself up and get really confused and have some very bizarre to track down bugs. So yeah, if your structs are small and only have value data like these two, then hey, it's a good time to use a struct. So just put that in as an example over here. So basically we have 4 pieces of data, or 4 components that describe these units or entities here: is alive, hit points, armor, and position data. And wouldn't it be extremely convenient to have all these various types of arrays be in some kind of structure like a dictionary, and we can set and access using generics and whatnot? So first of all, you could actually implement this yourself. Some of the code we did for the events and callbacks tutorial would basically give you all the tools you need to build something like that. But that's basically what the entity component system does for us. Instead, it's got this sort of generic structure where you're writing a function, like it's something like entity manager dot set component. Again, I'm sort of making up the syntax on the fly. It's something like this, and then you have some sort of ID, your index of your entity, and then it's a generic. So you're saying something like set component using unit position data to some data goes there. So you're doing that, and then so instead of having to reference this directly, you can do this, and it makes it more flexible because it's generics and yada yada yada. So that's what the ECS is going to do for us. Anyway, so here's an example function for if we want to create a new unit in the game. It first finds out if we're out of space. So if our current capacity is less than our first empty index, then we will grow. If we check to see if we have any dead units. If we don't have any dead units, we will grow the array. Otherwise, we find the first dead spot, we flag it as being alive, and we return the index of the dead spot. These are all integers, so we just return the integer that describes the unit's ID. So all units will always be referred to as their ID, and the entity component system works like that. It's got, I don't remember what it's called. It does have a class or a type to refer to the entity ID, but it's basically just an int. It's the int that is the index of it in the array. If we're not full, then we just grab the first empty spot, we flag it as being alive, and we return that index number and increment the index number. If we kill a unit, what we do is we just flag that unit, so is alive I, we flag it as false, and then we make sure to queue it up to the list of dead units so that we can recycle it later. And here's an example of our accessor, because we aren't using generics and things like that. We would have to write a bunch of accessors for getting and setting the various components, like unit hit points over here. So we want to set the hit points of units with this index to be equal to H. So here we do a little sanity check to make sure we're not out of bounds, and we set the hit points for unit at this index to be equal to H. Again, rewriting this as generic stuff would be kind of swell. And then here's the grow unit array function here. So if we're at size 0, then we just instantiate all 4 arrays to this size. Again, would be really nice to use some sort of dictionary or something so that we don't have to write code like this that we then have to update whenever we add a new type of component or property to our entities. We wouldn't have to do that. So hint, hint, that's another really good thing. Otherwise, we just grow the array. And this is example code. Technically, it should vaguely work, but is just here as an example, not necessarily an example of what should work. So this is a function to help you resize an array to a new size. It creates a new array of this size and then copies the value of your old array. And then because we pass it as a reference, it's able to give you the new pointer. Anyway, whatever. And here's an example okay, of processing data. It's very similar to what we were looking at before, okay, where we're just looping through everything in all of our entities. We're looping through based on the size of the arrays, which we actually could be looping based on, what is it, capacity? What did I call it? Current capacity. There you go. I'll do this instead because it's a little less confusing. Although all the arrays' length should be equal to the current capacity. So we're going to loop through each entity in our array. First, we're going to check to see if entity I is alive. If it's not, we will do a continue, which just starts to the next loop right away. Then we're going to loop through all the j's, check that they're alive, and if both I and j are alive, then we'll check to see if one's higher than the other and presumably do more than that. This would be very, 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 very fast because we're simply interacting. We've got two arrays. We're interacting with is alive and position data. It's all contiguous data. None of it is a reference that points to something else. Again, is alive I might be in a different block of memory than is alive j, and certainly these will be in different blocks of memories than position data I and position data j, but your cache can have multiple blocks of data in it, and most likely it will be able to keep most, if not all, of this information in the cache and or load it from RAM in really optimal and friendly ways. And this should work pretty fast. Again, I checked the comments. There's probably going to be some people pointing out some even better ways to optimize the cache performance and things like that. But, you know, it's pretty good over here. So that's an example. And what's cool about this, with this hint, is this function only operates on a single piece of data. Well, technically two pieces, because it checks the is alive status first, and the position data. And other functions might operate on other completely independent pieces of data. And also, this is read-only, right? Like, we're only reading. If another function was also only reading from is alive and only reading from position data, there's no reason both those sets of functions couldn't run at exactly the same time, right? It's perfectly thread safe to have two separate threads read from the same data. The only thing that's unthread safe is to change data. If you're changing some piece of data that's important that no other thread is also trying to read or write that same data. Otherwise, weird, bizarre things can happen. But this means this function here, an update example, there's no reason that this couldn't be offloaded to a job, a thread, and run concurrently with some other job, some other thread at the same time. Not only does it run very fast because of our sort of general cache optimization, but it's very safe for us to go and feed off to a thread. So that's the entire buildup that we're getting to here. In the next video, what I want to do is I want to cover the Unity job system. And again, that's going to be an example of something that you can use today. Even if you don't do a lot of the other data, or any, in fact, of the new data sort of refactoring over here. Even if you're just using regular old game objects and whatever, the Unity job system is a great and handy way to spawn off multiple threads to handle some jobs. And again, I think the name job really emphasizes the use case for that. You're not generating a thread that's running concurrently side by side the main thread for the lifespan of your program. You're creating specific jobs that have a clear beginning and a clear ending. Sometimes the point will be to run multiple jobs at the same time within a single frame, right? Start of a frame, I'm going to spawn 4 jobs, I'm going to wait for all 4 jobs to be done, and then we're going to continue on with running the update for that frame now that all that data has been crunched simultaneously. Or sometimes it'll be a job where, okay, this is going to take multiple frames, I'm going to start it now, and X number of frames later when it's done, either we'll get signaled or we'll check to see, if that job is completed, at which point we will, do something based on whatever numbers it just crunched for us. So the job name really has that emphasis in there. And so that's the plan of what we're going to look at next. Thanks for watching this. I know we covered a lot of things. Some of it had to be geared towards beginners and some of it is probably well beyond beginners. Hopefully we sort of did an okay job explaining everything as much as possible. I am going to go and put this code up on GitHub like the others, although again, none of this code is intended to really run or do anything. It's all example stuff with lots and lots and lots of commentary here. But again, you can use some of this to speed up your programs today. And also, this should get your brain ready for the new paradigm of designing stuff with the entity component system, which you're not going to have to use all the time. Right? There's plenty of times where the entity component system and this data layout and jobs are not going to speed up your program at all. You'll get no performance gains, and instead what you're doing is you're sort of going out of your way to not use object-oriented stuff that might make it easier for you to write cleaner code, right? Data segregation and having one area for your data versus another area for the game logic, really good all the time. except for the most trivial of examples. But that doesn't mean you can't use classes and objects to represent your data, right? You don't have to necessarily use these sort of individual little arrays to still do that segregation. But if you are running a lot of objects and you are finding yourself have to iterate over large arrays every frame, making some sort of move like this is actually going to be huge. You could use traditional game objects too. Like after all this is run, so what you could do is you could start, all right? If you were running, you had a typical Unity program where everything's in a game object. Actually, I'll write that. If you are using a typical Unity setup with traditional game objects, you can still do something like this by doing, so first you would set up a new array. So let's say you set up an array, vector3 position data equals new vector3 array, which is equal to number of game objects. Then you do something like for each game object geo in relevant game objects, you know, sort of pseudo-quish over here, like this. Then you're going to do something like position data. I guess I'm not indexing correctly, but you know, some index is equal to game object dot transform dot position, right? You're doing something like this. I mean, I know it does whatever. Anyway, so you're going to populate it. So you put everything from the game objects into an array. Like this doesn't take that long. And if this is enough data, it might be worth for the processing to avoid all the cache lookups, to just dump it in here. And then afterwards, over here, copy the position data back into the game objects. Alternatively, you could always have the permanent position data array somewhere. And what happens is that every update, each game object looks up its position in the one position array and sets its, you know, transform.position that way every update. So that way it avoids the copying back and forth. So there's ways to use this technique. Get rid of that. There's ways to use this technique even with a sort of a traditional setup. And in fact, you probably aren't going to exclusively use ECS for everything. Even if you go and commit whole hog, there's still going to be some things that are better at game objects, some things that don't need to be made into components. Certainly all your UI elements and things like that. But there might be other like standalone singleton stuff that doesn't get applied into the component system, and doesn't win you anything. Boom. There we go. Get rid of that. Okay, I think we're back to where I want it to be. Excellent. Okay, that's it. Thanks for watching, and we'll see you next time.